This will be our topic 4A5, population interactions, and we'll be talking today about R-selected and K-selected species. Exponential and logistic growth is going to be the primary focus. We'll also do some density-dependent and density-independent factors. So whenever we talk about population growth, we almost always do it in an idealized situation, and that's what we'll be talking about today. A couple of specific examples. So the only thing that's going to affect increases or decreases in population are going to be immigration into the population or immigration out of the population, and then the birth rate and death rate. So if we ignore immigration and emigration, we're really looking at growth rate being the difference between the birth and the death rate. So one of our goals is in human populations has been for a number of years to do what's called zero population growth, and that's where we have an equal number of births and deaths. So this particular formula right here, you are going to need to know. You will have some calculations that are based on it. Not too complicated though. And when we have a population that is exponential, we are going to have a different equation, and you'll see that down here. So here are two different populations with different exponential growth patterns. You can see one of them grows a little bit more slowly, and the other one grows a little bit more rapidly. And we will see both of those cases in any newly established population. So what happens in an exponential curve is it does look like a J, and that happens with populations oftentimes that are rebounding from a major loss, such as the example we see here from a particular elephant population that we have been started protecting in the 1960s, and what you see on the graph here is once we started protecting these species, even though they are relatively long-lived species and reproduce fairly slowly, we have an exploding elephant population in certain parts of Africa. So the point here we want to look at is what's called carrying capacity. And carrying capacity is the ability of the environment to maintain the population without the environment being degraded. Species that exceed the carrying capacity are going to cause degradation to the environment. Species that are below the capacity are going to allow the environment to maintain its diversity and stability. So the second type of growth you can have is called logistic, and again, slightly different formula for logistic, because what we get is we get a difference in the shape of the graph as it approaches a carrying capacity, and that's what we see down here in the graph. This one doesn't make a whole lot of sense. I do have it on there because it can be graphed very easily. Every exponential growth curve that you see here is always at some point going to level off or crash. So it is going to drop down like this. So these are going to be species which have a rapid growth, but they typically also have a rapid decline. So they're much wilder in the variations in their population size. Alright, so if you look at paramecium in this next picture, we'll see what we're talking about here with an S-shaped curve right over here on the right. And what we see is the very much over time a movement just above and below the carrying capacity for them in the particular environment that they're in. By comparison, Daphnia, which is a water flea, you can see here they exhibit both an exponential growth curve and then coming back down to a logistic growth. So they would exhibit the J-shaped population in the beginning, and then they would have a population crash. That'd be fairly significant over a short period of time, and then they would rebound. So that's what we're talking about with the Daphnia population there, and again a larger graph of the same thing. And now here we're going to have it. This is the ones that are going to go much above that, and they're going to be the ones that are have very high fluctuations between the population high and low, and very difficult to actually have a K situation there, right? And of course, the logistic growth model itself doesn't really actually fit any real populations over a short period of time, but may allow us to predict what's going to happen over longer periods of time. So K-selected species, those are going to be species that are density dependent, and they are going to be sensitive to population density. They are going to be fluctuating at or near the K, which is the carrying capacity. R-selected species are not going to be fluctuating near the K. They're going to show a great effect of ability to change, so increase in population and then a rapid decrease in population. So R selected ones are going to have an up and down kind of curve, and the K selected are going to have that S-shaped curve, very similar to what we saw in the exponential or logistic growth curve. So these are again gross oversimplifications, but they do make it useful for us to do things like predict populations of flies or mosquitoes or relatively short-lived species that are dependent on weather and other contributors to their population size. Now, what are the factors that might affect a population, and what are some of the things which are going to allow these populations to show these big fluctuations? So density-independent populations, as we mentioned earlier, their birth rate and death rate don't change with the population density. They're going to be, again, they could be very high death rate or a very low death rate, depending on the environmental conditions. And these guys have rise and fall with population density. And we can see again both birth rate and death rate vary. If the death rate is constant, which we see in this one, and the birth rate varies, then what you're going to get is a density-dependent curve right here. And if we have a density-independent one, the death rate may vary, but the birth rate remains constant. And as the death rate decreases, the population size would increase. So some stuff about density dependent, that would be stuff like competition. You know, if you need food and there's high competition for food, it's going to limit your population size, territories, and again, all the kind of typical things you would think of for density dependent, keeping the population size check. So the biggest one is competition for resources. As population density increases, competition also is going to increase, and that is going to decrease the success or reproductive success of the individuals in the population, and then that itself can then cause a decrease in the population size over time. And again, territoriality. Cheetahs are highly territorial. If you cut down the amount of places where cheetahs can live, then they are going to have fewer cheetahs. And that is exactly what's happened with the cheetah population. The places where cheetahs can live is so limited that their population sizes are so small because their territories are so large. They're a high risk for extinction. And territoriality and nesting behavior, we see here the gannets, they are picking the best spot, and of course the birds who get the best spots are going to get the most opportunities to mate. Alright, and finally some other stuff that we're going to see here. Population density allows us to increase the number of pathogens. If you read Guns, the Jared Diamond book, you're going to see that Guns, I can't remember the rest of it, they're going to have these evolution of these diseases that only spread in large populations. So once we started forming cities, Guns, Germs, and Steel, there we go. Once we started forming cities, then we all of a sudden saw this increase in the increase in these massive diseases. As the populations are less dense, you get fewer of those. So that is one of the population control mechanisms. Obviously, prey population, that if it rises, the predators are also going to rise, and that's going to affect or control the prey population and the predator population. Obviously today we're worried about toxic waste, and that can also do it. So the more toxic waste you have in an environment, which is the result of overutilization of resources sometimes, that is going to limit your population size.